Hi, I'm Yu. Today I will talk about sublinear time hypergraph sparsification via cut and edge sampling queries. This is a joint work with Sanjeev Khanna and Ansh Nagda. So let's start with what is a cut sparsifier. Given a graph G, a 1 plus or minus epsilon cut sparsifier G prime is a sparse subgraph that preserves all cut values in G within a factor of 1 plus or minus epsilon. So let's look at this example in the picture. So in the original graph on the left, the cut contains 5 edges, so the cut size is 5. And in the right-hand side, in the sparsifier, there is only 2 edges across the cut, but their weight is 2 and 3. And thus, the sparsifier preserves the cut size of the original graph. Cut sparsifiers are usually used as a way to improve the performance of graph algorithms. So imagine the following scenario. So suppose we have an algorithm A that solves a graph problem, but it is very slow running on a dense graph. But in this case, maybe what we can do is we can first compute a sparsifier G prime and run algorithm A on G prime, which uses less time, and get an approximate solution. So the quality of a cut sparsifier is the number of edges in it. The concept of cut sparsifier can also generalize to hypergraphs. So in a hypergraph, a hyperedge may contain more than 2 vertices, and then the size of a cut is the total weight of hyperedges crossing it. Similar to the case of normal graph, given a hypergraph H, a 1 plus or minus epsilon cut sparsifier H prime is a hypergraph that preserves all cut values in H within a factor of 1 plus or minus epsilon. So for example, in this picture, in the original graph on the left, there are 4 hyperedges crossing the cut. And in the sparsifier on the right, there are only 2 hyperedges crossing the cut. But now each hyperedge has weight 2, and thus the sparsifier preserves the size of the cut. In our recent work, we show that any hypergraph has a 1 plus or minus epsilon cut sparsifier that contains about order n hyperedges. However, since any subset of the vertices can form a hyperedge, a hypergraph could have up to 2 to the n hyperedges. That means we might need to take exponential time to read the whole graph. So the natural question is, can we construct a hypergraph sparsifier in sublinear time? So more specifically, suppose the graph has n vertices. Can we construct a hypergraph sparsifier in poly n time? And it is regardless of the number of hyperedges. To answer this question, like many other sublinear time problems, we need to first consider how do we access the graph. In this work, we consider the query model and allow in the following 2 queries. The first one is the cut size query. It allows us to query a cut and return the size of the cut. And the second one is the cut edge sample query. It also allows us to query a cut, but then it returns a random hyperedge crossing the cut. And in this work, we prove that there is a polynomial time algorithm that constructs a hypergraph cut sparsifier using cut size queries and cut edge sample queries. And as a complementary, we also prove that there is no polynomial time algorithm that can construct a hypergraph cut sparsifier that only using cut edge sample queries. And in the rest of the talk, I will introduce the ideas of proving the first theorem, which is how to construct a hypergraph sparsifier using cut size and cut sample queries. We first review the definition of edge strength, which is a very important concept in graph sparsification problem. So a k-strong component of a graph G is a maximal vertex-induced subgraph of G that has minimum cut at least k. And the strength of an edge E, denoted by ke, is the maximum value k that E is contained in a k-strong component. And it is a well-known result that the sum of weight over strength over all edges is at most n-1 for any graph. And notice that the definition of strength and the upper bound on the sum of weight over strength also holds for hypergraphs as well. In a previous work, Koga and Cross-Grammar proved that for any hypergraph H, if we sample each hyperedge E with probability PE at least a constant C times n over epsilon square times KE, and give weight WE equals 1 over PE if it gets sampled, then the resulting graph is a 1 plus or minus epsilon cut spacifier of H, and it has order n square hyperedges. So we will implement this algorithm, which means we need to sample each hyperedge E with probability at least PE equals omega n over KE. And the main challenge is we do not know the KE values, and computing them will require knowing the entire graph. So let's consider the following meta-algorithm. Given a graph, we first find the minimum cut. Let's say the minimum cut is S and V minus S. And then we sample about n edges crossing the cut and add them to the spacifier. Then we will repeat the same process on the hypergraph induced by S and V minus S. Like on S, we will also first find the minimum cut and sample about n edges crossing the cut, and then add them to the spacifier. Also, likely on V minus S, we also do the same thing. First find the minimum cut and sample about n edges and add them to the spacifier, and so on. Now, let's focus on an edge E. We look at the time when it has a chance to get sampled, which means it is contained in the minimum cut of some induced graph which the algorithm encountered. Notice that the cut is the minimum cut of an induced subgraph, and this induced subgraph also contains E. So the strength of E, KE, is at least the size of the cut. So this means that for each edge E, it gets sampled with probability at least n over KE, which means the algorithm does construct a cut spacifier. Now let's try to implement the meta-algorithm with cut size query and cut sample query. So in the first step, we want to find the minimum cut of the graph. It is well known that the cut size is a submodular function in normal graph, and it is also true in hypergraph. So in order to find the minimum cut, we can run the polynomial algorithm for submodular function minimization with cut size queries. And for the second step, we want to sample about n edges from a cut. And the cut sample query does exactly this. And in the end, we want to repeat the process in both induced graph S and V minus S. Now the question is, can we implement the cut size query and cut sample query in the induced graph? Unfortunately, the answer is no for hypergraph. So let's consider the following two examples in the picture. So the first graph on the left is a rank 2 clique of 4 vertices, where the rank of the hypergraph edge means the number of vertices in this edge. In other words, rank 2 means the graph is a normal graph. And the second graph on the right is a rank 3 clique of 4 vertices. It means every edge contains 3 vertices. It is not hard to see that every cut has the same size in both graphs. If the cut has 1 vertex on the one side and 3 vertices on the other side, the cut size is 3 in both graphs. And if the cut has 2 vertices on both sides, then the cut size is 4 in both graphs. So this means that if we only use cut size query, we cannot distinguish between these two graphs. But on the other hand, if we consider the induced graph with two vertices in both graphs, in the first graph on the left, because there is an edge in the graph, the minimum cut size is 1. And in the second graph, we have no edge in the induced graph, and so the minimum cut size is 0. This means that we do need to have a different answer if we do cut size query in this induced graph of two vertices. So we cannot simulate cut size query in the induced graph. However, in the case of normal graph, we do have a way to simulate cut size query in the induced graph. So let's consider this graph in the picture. The cut A and V minus A contains edges between A and B, we call EAB, and also the edges between A and C, which called EAC. And similarly, the cut B and V minus B contains EAB and EBC, and the cut C and V minus C contains EAC and EBC. So suppose the induced graph is defined on vertex set A union B, and we want to know the cut size between A and B, which is exactly the size of EAB. The answer is half of the cut size of A and V minus A plus the cut size of B and V minus B minus the cut size of C and V minus C. The main reasons that this approach cannot be generalized to hypergraph cases is that in the case of hypergraph, there are edges that contains vertices in all of A and B and C. And let's call these edges E, A, and B, C. And in this case, the cut size of A and V minus A plus the cut size of B and V minus B minus the cut size of C and V minus C is 2 times EAB plus EABC. Note that the size of EABC might be much larger than the size of EAB, and thus this approach won't give good approximation either. But however, it turns out that this quantity is still very useful in our problem. And the idea is, since it is impossible to simulate cut size query in the induced graph, so why don't we change the object we consider and change into an object that we can easily calculate even in the induced graphs? So we will change the definition of cut and strands a bit, and we will name them pseudo cuts and pseudo strands. So we define the pseudo cut size of a set S in an induced subgraph GX as delta XS equals half of the cut size of S and V minus S plus the cut size of X minus S and V minus X plus S, and minus the cut size of X and V minus X. So with the definition of pseudo cut, naturally we will define the pseudo strands of a hyper edge E. We call that K prime E as the maximum value K, such that E is contained in an induced graph with minimum pseudo cut size K. There are some nice properties of pseudo cut size and pseudo strands, which is similar to the real cut size and strands, that will help us to construct the sparsifier. And these proofs are quite technical, and I will not cover them in this talk. So let's look at these properties. First, for any induced graph, the pseudo cut size is a submodular function, just like the real cut size. So this will allow us to use the submodular function minimization algorithm to find the minimum pseudo cut in an induced graph easily. And secondly, we can show that for any hyperedge, the pseudo strength is at least as large as the real strength. And also it is not larger than n times the real strength, which means for any hyperedge E, Ke is smaller or equal to K prime E, and which is smaller or equal to n times Ke. So this means to construct a hypergraph cut spacifier, it is sufficient to sample each edge E with probability at least n squared over K prime E, because it will mean that we will sample each edge E with probability at least n over Ke. So we modify the meta-algorithm as follows. In the first step, we find the pseudo-minimum cut of the graph instead of the real minimum cut, which is delta xs. And then in the second step, we will sample about n squared edges in the pseudo-cut and add them to the spacifier. And then we repeat the same process on hypergraph induced by S and X minus S. And as we see earlier, we can use cut size query to simulate the first step since the pseudo cut size is also a modular function. But now the real problem is, in the second step, how do we actually sample edges in a pseudo cut? A key observation is on an induced graph Gx that is encountered during the execution of the algorithm. And I want to emphasize here that we are not considering every induced subgraph, otherwise, in this case, the probability would not be true. And we only consider the ones we encountered in the algorithm. So in these induced subgraphs, we have the probability that the size of the minimum pseudo cut, say delta xs, is at least 1 over n fraction of the cut size of S and V minus S. Now, using this lemma, we can sample edges in the pseudo cut by just sampling from the real cut of S and V minus S by cut sampling queries, while we will oversample with a factor of n. And this finished the last piece of our algorithm. So in the final algorithm, we will change the second step as follows. Instead of sampling n squared edges in the pseudo cut, we sample n cubed edges in the real cut S and V minus S, which is given by the first step. Now, the whole algorithm can be simulated by cut size queries and cut sample queries. And we are also guaranteed that each edge E gets sampled with probability at least n over Ke, which means we indeed get a cut spacifier. And also notice that the process is at most recursive by n times, so the running time of this algorithm is also polynomial in n. After running the algorithm both, we will get a spacifier with polynomial and hyperedges. Although the size of the spacifier might be still very big, we can further run the cut spacifier algorithm of our previous work on the resulting graph without doing any queries. And by doing so, we can further reduce the number of hyperedges in the spacifier to O to the n. And this concludes the main idea of the algorithm to construct the cut spacifier using cut size queries and cut edge sample queries, which is the main result of this work. In conclusion, in this work, we give a sublinear time algorithm for creating a hypergraph sparsifier using cut size queries and cut edge sample queries. And we note that it is also possible to achieve a similar result if we replace edge sampling queries with another natural query, which samples the hyperedge that contains a given pair of vertices. And one can think of this query as a generalization of both pair query and neighbor query, which are two mostly used query models in the normal graph case. And finally, we also note that our algorithms can all be generalized to construct the hypergraph spectral spacifiers as well. As for further direction, it remains to fully understand the power of cut-size queries alone. On one hand, one can show that they cannot be used to create a hypergraph cut specifiers. Actually, by the example we see earlier that cut size query alone cannot distinguish between the case of rank 2 for click and rank 3 for click. However, it might be possible to create a data structure that can return the size of any cut of this graph approximately. And the main difference is, in this problem, we are not required to only use the hyperedges in the original graph. And thanks for listening.